All right, so hi everyone, I'm Camille Krewcun, as Hugo presented me, and I'm a third-year PhD student, and I'm going to present you SOFA implemented method for state expansion simulation with an experimental validation. So this presentation will be composed of 5 parts. First, I'm going to talk about the medical context of our study. Then I'm going to present you key aspects of our simulation strategy in SOFA. In third, I'll detail the experimental protocol we conducted to validate the simulation. And then I'll show some results and I'll conclude. So regarding the medical context, we are talking here about coronary arteries and coronary stents. So if you're not familiar with this, the coronary arteries are located in the heart, and they are the small vessels in charge of providing the heart muscle, the myocardium, with blood. So concretely, they are responsible for your heart pumping correctly. And one of the main issues that can occur with these arteries is a disease which corresponds to the development of a plaque inside the artery wall. So what happens is that with a healthy coronary artery, the blood can circulate freely in the artery lumen and reaches the heart without problem. But in a diseased artery, the growth of the plaque obstructs the lumen and therefore reduces the blood toward the heart. So the consequence is that the heart tissues suffer ischemia, necrosis, and eventually, if the situation settles for too long, the risk is to have a heart attack and to die. There are several options to treat this, but the one I'm interested in uses a small medical device, which you can see here, and which is called a stent. So as you can see, it's typically made of metallic thin wires, and it has the shape of a cylinder to match the shapes of the coronary arteries. So the one you see here is expanded, but initially stents are crimped on a deflated balloon at the tip of a catheter. And the idea of the procedure is to place this catheter where the plaque is located in the artery and inflate the balloon. This has 2 effects. The first one is that the stent is expanded, and the second one is that the plaque is compressed, allowing the artery to retrieve a correct diameter for blood circulation. An important point here is that once the balloon is deflated, the stent stays in the artery. It's a device that patients keep for the rest of their life, and therefore the deformation of the stent is definitive, is permanent. As you can imagine, this procedure is mostly non-invasive, so it means that it is less traumatic for the patients, but the drawback is that the clinicians don't have access to many information regarding what's going on in the artery during the procedure. Therefore, the idea of our simulation is to provide them with a reliable visualization and prediction tool for this procedure. So how do we do that? I'll present here 2 main aspects of our simulation. And the first one is the discretization of the stent using plastic beam elements. So very briefly, beam elements are one-dimensional elements which are used in finite element methods to represent 3-dimensional slender structures in which 2 dimensions, typically the dimension of the section, are much inferior than the 3rd dimension. So it's the case, for instance, for the stent wires, the stent struts, as you could see on the first picture. There is already a component implemented in SOFA, which is called the beam FEM force field, which implements elastic beam elements. So what we did was to inspire from the general structure and the general characteristics of this one to create a new component, which we called the beam plastic FEM force field, and in which we implemented a plastic mechanical behavior, which is so nonlinear and which allows to represent permanent deformation in a mechanical way. So for this, we used the von Mises plasticity model, either with perfect plasticity, which is a simplified model, or with linear mixed hardening, which is a bit more realistic. And as Hugo just said, this was pull requested yesterday, and it's one of the contributions you can vote for. So if you want to have more information or to have a look, feel free to do so. So once we have the beam elements, the discretization of the stents uses 3 steps. First, we realize micro-city acquisition of a real stent, of a commercialized stent, in order to retrieve three-dimensional images of the stent geometry. From these, we can conceive then a flat version of the mesh composed of edges and nodes. And to do so, we use computer-aided design software, like SolidWorks, for instance. From this flat version, the last step consists in importing the geometry in SOFA, wrapping it in the shape of a cylinder, and converting each edge of the topology to a plastic beam element. So what we obtain in the end, and what you can see on the picture on the right here, is a three-dimensional mesh representing the stent, and which is composed of plastic connected beam elements. Once we have the stent in the simulation, the second thing we have to do is to model the balloon inflation. And for this, we chose not to represent the balloon explicitly, but to develop a virtual membrane model. For this, we took the pressure to diameter data that is provided by balloon manufacturers, and we applied it to our virtual membrane so that the virtual membrane would undergo the same displacement in the simulation as would do a real balloon in a real life situation. The only difference here is that instead of pushing the stent from the inside, as would do a real balloon, we pull it from the outside by attaching the virtual membrane to the stent using stiff springs. So of course, this is an approximation, but it's much less costly than what would represent the inclusion of a real balloon model in the simulation. So once we have this simulation methodology, what we have to do is make sure that it is good enough, that the approximation we use are good enough to actually represent a real stent deployment. And for this, we deployed stents in silicon phantoms of coronary arteries. So the first step of this was to build these phantoms. And for this, we 3D printed molds in two parts, an external part, which you can see here in gray, and an internal part, which you can see here in white, and which is made of a water-soluble material. The idea here is that once we open the mold with the cured silicon, the fact that the inside material representing the lumen is water-soluble allows us to just put it into water and wait for it to dissolve. And then we obtain a hollow silicon model of artery. Here, for instance, with a bifurcation, and here in a more simple straight configuration. Once we have these phantoms, as I said, we can deploy stents in them. And for this, we use once again micro-city supervision, this time to get 3D images of the stent geometry at different steps during its deployment. And the idea then is to compare these geometries with the configuration we obtain by running simulations, which reproduce the conditions of the experiment. The comparison is simply made with rigid registration, and you can see here an example of the superimposition of simulation data and in red and CT data in gray. So regarding our results, we conducted this experiment on 9 different stents in 9 different coronary artery phantoms, with increasing curvatures in order to get closer and closer of realistic, at least, artery geometries. So I'm going to show you a short video clip of what we did. If it works, let's hope it does. All right.
Yeah, we've got the same issue as during the test that we had. I'm gonna share with you guys directly the link of the YouTube. Can you share your screen, maybe, Camille, so that we see we can see the video, and in the same time I give you the YouTube link in the audience, so that if you wanna see the video, I'm gonna open myself the video in a widget. So yeah.
Okay.
We see the different. Okay. It was in
so
different vessels.
So I'm going to be very short on this. Okay, so this is 9 geometries I was talking about of arteries. This is the simulations I was talking about, and you can see here in these arteries stents expanding right there, and they switch from red to blue, indicating that we switch from a small deformation at the beginning to a more important plastic deformation represented by the blue color. Okay, so I'll leave this quickly. And yeah, you go share the link. So if you want to have a look at it later, you will be able to do so. Let's stop this. All right. So once we perform these simulations and the corresponding registration, what we do is we compute two quantities on the registration. The first one is the Euclidean distance between points of the simulation and points in the CT. And you can see here that for all stents, the mean Euclidean distance is under 300 micrometers. And the second quantity is the difference of radius, once again, between the simulated expanded stent and the CT data. And here you can see that in average, it is inferior to 100 micrometers. So these are satisfying for us because it is close to the lowest dimension of our problem, which is the stent strut thickness, and which is typically around 100 micrometers, depending on the stent model. So what this means is that we are able to reproduce a real-life stent expansion with our simulation with a precision in the same order of magnitude as the stent wire thickness. So in conclusion, very quickly, we did validate our model in nine in silico experiments, so which is a first step in full validation. And for this, we obtained computational times inferior to what we find in literature for fully volumic simulations. However, our computational time is still not compatible with clinical use, and we did not perform any optimization at the moment. It runs on a single thread and sequentially. So this is a very next step of our work. And in the long term, we are planning to use medical images of the inside of the arteries, in this case, optical coherence tomography images, to introduce patient-specific artery geometries in the simulation. All right. Well, thank you for listening to me. And if you have any questions, then I can answer them.
Thank you, Camille, for the presentation. Is there any question for Camille? So I see a question from University of Catalonia, I think, incoming. Christian as well. So do not hesitate to type, guys. If the question is Christian, congratulating you. So you're basically able to load different shape of stent, right?
Yeah.
But is the process automatic or?
The discretization of the stent is not automatic, so we have to treat each stent model separately, and it represents like 1 or 2 days of preparation. But once one stent model, one stent brand, let's say, is implemented, we can reuse it with any stent of this brand, any dimension, basically.
Mm-hmm. There is the question. So from I don't remember. Mr. Suda, your first name, I don't remember, sorry. Yeah, so is that nitinol that you are taking as a mechanical properties?
Yeah, so in this case, no, it's not nitinol. Nitinol is a shared memorial, as you said, Eduardo, and it's therefore, it doesn't present plastic deformation in the same way here the balloon expandable stent do. So, no, it's mostly they are made of how do you say, stainless steels, alloys such as cobalt chromium or platinum chromium, and for this reason they undergo plastic deformation.
Christian, feel free to take the mic if you'd like. I think there are other applications of the use of plastic deformation in SOFA. Yeah, definitely. Have you something in mind already, Christian, or? We'll see that. So, yeah, okay. But if you have an idea of application that you are thinking about and you'd like to share, do not hesitate to write that, or to contact Camille afterwards if you prefer. Thank you, Camille. Is there any other questions? So Guillaume, I see, is starting typing. Do you want to ask, Guillaume wants maybe also to ask a question. I don't know, anyone can please, put something in the chat. Otherwise, what did I write as well? Yeah, it was the question, when I think it was slide 37, where you had a comparison between the two shapes. What was the error coming from, and what was the level of where you could see improvements in the model. But maybe we'll discuss that in the breakout room. I'm going to join you.
Yeah. Okay. Yeah.
Okay.
Sure. Okay. Thank you, everyone.
Eric said, I couldn't see when you import your model what average is the size of your model.
Yeah.
How many teams?
Yeah. Very quickly, it's around a few thousands of elements. So for the smallest beams, it's around 1,000, and for the longest, we had around 3,000 beam elements.